Okay, hi everyone. So today we're going to cover two related things. One is a concept called projection cost preserving sketches, which is another way to do sketching to speed up low rank approximation, but it can actually do more. And one of the things it can do more is it can be applied to, for example, k-means clustering. And we'll talk about that as well today. This is also sometimes called PCP sketches, which may be a little bit confusing because in the theoretical computer science literature, there is another PCP theorem, which is probabilistically checkable proofs. And as you might imagine, this PCP has nothing to do with that PCP. Okay, so let's get started. So PCP sketches. This is a concept that was introduced not that long ago. It was by Cohen, Elder, Musco, and Pursue in 2015. And actually, it's a story that is somewhat connected to this course. So the first time I taught a course that covered sketching topics was fall 2013, before I joined Berkeley. And it was not exactly the same course as now. I mean, the topic selection was a bit different, but it still had a lot of overlap. Anyway, at the time, Elder, Musco, those were three students who were in my course. And Musco had a final project that was related to what you're going to see today. It wasn't exactly the same. And then later they developed it further with Elder and brought in two other grad students. All of them were grad students at the time this was written. They brought in Cohen and Pursue as well. And then they used this, which was published, I think, in Stock 2015. So just some motivation for you all as you're working on your final projects. There are actually quite a few examples of I think pretty nice papers that came out of final projects. Maybe at the time the final project was submitted at the end of the course, at the end of the semester, it wasn't quite publication ready. But then students took it home after the semester was over, thought about it a little more, refined it a bit, maybe brought in their friends, and then got some, pushed it to be something really nice and ended up getting a really nice paper. I mean, now PCP sketches, I would say, are a pretty foundational thing in sketching for linear algebra. So what is a a projection cost preserving sketch? Okay, so it's like the name suggests, sketching that preserves the costs of any projection. Okay, so the definition, let's say, so for us now, A is just going to be some given matrix. Okay. I'll say that pi is, let's say it's an M by D matrix, is an epsilon K projection cost preserving sketch for A if for all projection matrices P in, I'll call it OK, this is the set of all rank K orthogonal projections. Okay. We have that if you look at the Frobenius norm squared of identity minus P, A pi transpose Frobenius norm squared. So here what I'm saying is look at the matrix A pi transpose, which I usually, it's just maybe it's what I'm used to. I'm used to thinking of matrices as linear operators when you multiply by the left. So if you take the transpose of A pi transpose, the transpose of A pi transpose is pi A transpose, right? So you can think of pi as sketching the rows of A. Pi is reducing the dimensionality of the rows of A. Okay. So take A, sketch its rows, project down the rows to a lower dimension using pi, and then now look at the error you get in Frobenius norm when you project down to P. So you look at A pi transpose minus P A pi transpose. Okay. And now what's the error that's left when you do this projection? I claim that, okay, not I claim, the definition of an epsilon k PCP sketch is that for any P of rank K, this is basically preserved as if you didn't have the pi. So it's at most 1 plus epsilon times identity minus P A for median norm squared, and it's at least 1 minus epsilon times the same thing, identity minus P A for median norm squared. Okay, does that make sense? So pi is a PCP sketch if it preserves the cost. You can think of, again, what is low rank approximation, right? Low rank approximation is we're trying to compute the optimal P, which is equal to, I guess, UK transpose, where if you write the SVD, A is U sigma V transpose. Right. So, right, we know that if you're actually trying to do unconstrained low rank approximation, find the best rank K approximation of A, we know from the Eckart-Young theorem, which we saw last week, that the best rank K approximation is the truncated SVD. If A is equal to U sigma V transpose, just get rid of the last n minus K rows of U and columns of U and get rid of the last n minus K columns of V. And you're left with a rank K matrix. And that rank K matrix is exactly the best rank K approximation. That's the Eckart-Young theorem, which is equivalent to saying project the columns of A onto using the projection operator, which is UK transpose. Okay, that's equivalent. So we know that this is the optimal P. So what PCP sketches let you do is they let you do sketch and solve for low rank approximation, right? Sketch and solve says, if I have some really high dimensional problem, what I'm going to do is project it to lower dimension, solve the problem in the lower dimension, find the optimal thing in the lower dimension, and then hope and lift it and say, this thing is nearly optimal for the original problem. We already saw that for approximate regression, right? We already saw sketch and solve for approximate regression. We said, look, if pi satisfies an epsilon subspace embedding, sketch and solve works. Or if pi satisfies a constant subspace embedding instead of epsilon together with an AMM, approximate matrix multiplication property, that was Charloche's analysis, again, subspace embedding, again, sketch and solve works. We also earlier in the semester saw that sketch and solve works for k-means clustering as well. If you remember when we talked about, and it's in the course notes, when we talked about k-means clustering, we said k-means can be rewritten in the following way, right? Which is like, for every partition, the cost of the partition is some sum of square distances, weighted square distances between points in the same partition. And we said, therefore, if you do JL and preserve all the distances amongst all pairs of points, the cost of any clustering is preserved. Therefore, if you do sketch and solve and do k-means clustering in the sketch dimension, the partition you find, the clustering you find, will be an almost optimal partition for the original k-means clustering problem. That was, we didn't use the phrase sketch and solve back then, but that's exactly a sketch and solve statement, right? If you preserve all partition costs, all clustering costs, then that means that if you optimally solve or approximately optimally solve the sketched version, then that solution you find is almost optimal for the original version. That's exactly sketch and solve. So what PCP sketches let you do is they let you do sketch and solve for a low rank approximation, right? So we'll just hit A with a pi transpose. We'll find the best or approximately the best low rank approximation to the sketched version, and then the projection matrix we find is guaranteed to be nearly optimal for the original problem. So if pi is an epsilon k PCP sketch for A, then if P tilde star, say, is the optimal projection for the sketched problem, and when I say the sketch problem, what I mean is A pi transpose, right? That's the sketch problem. Then exactly the same analysis as what we did before for regression. When we first talked about regression, you'd get something like the identity minus p tilde star a for Beani's norm squared is at most 1 plus epsilon over 1 minus epsilon times identity minus p star a for Beani's norm squared. Does that make sense? So if you optimally solve the sketched version, you would have a near optimal solution for the original version. We saw this already when we talked about regression, right? The argument is basically saying, like, the argument was something like, so recap of why. This is something you've seen already, but just to make sure that it's drilled in your head. What do we know? We know that 1 minus epsilon times identity minus p tilde star a for Beani's norm squared is at most the same version but with the pi. Right? That's because it's a PCP sketch. The PCP sketch says that pi preserves the cost of any projection up to 1 plus epsilon. In particular, look at the projection p tilde star. And then now, I guess I should have drawn that in the opposite. Oh, no. Good. So now what do I know? Now I know that for the sketched version, p tilde star is better than p star because p tilde star is the optimal for the sketched version. So this is at most identity minus p star a pi transpose for Beani's norm squared. And then now again, I use the PCP sketch property to say that pi preserves the cost of any sketch. So in particular, pi preserves the cost of any projection. So in particular, p star. So then this is at most 1 plus epsilon times identity minus p star a for Beani's norm squared, right? And then you just move things around and you get exactly what I said. If you just take this and you compare it with this, you divide both sides by 1 minus epsilon, and you get that sketch and solve works. Okay. So that's PCP sketches. And I want to say one more thing about them before I go forward into proofs. I want to tell you that PCP sketches are more powerful than just unconstrained low rank approximation. They also let you do constrained low rank approximation. Okay. So suppose RK is a subset of OK. Remember, OK was like the set of all rank K projections. So now let's take constrained low rank approximation, where I want now P star to be the minimizer over P, not all rank K projections, but only those that are in RK, which is some subset of rank K projections. Okay. Then if you do the sketched version, you apply pi transpose on the right, you solve the sketched version, you get some p tilde star. Again, p tilde star will be approximately optimal by the same exact analysis before, because pi doesn't just preserve everything in RK. Pi preserves everything. It preserves everything in OK. So in particular, it preserves everything in RK. So if you solve the sketched version, whatever thing you find in RK for the sketched version will be approximately optimal for the original version. Okay. And what's one place where constrained low rank approximation shows up? K-means clustering. Okay. So note, this captures K-means clustering. Okay. Why might you ask? Let's remember what K-means clustering is. Let's remember what K-means clustering is. We're given points x1 up to xn that we're trying to cluster. They're in D dimensions. And also an integer parameter k, which is the number of clusters. And we want to find cluster centers y1 up to yk, which minimize the following expression. The sum I goes from 1 to n, the min over j from 1 to k of xi minus yj L2 norm squared. In other words, for each point, we look at its square distance to the closest cluster center, and we sum up those things. Okay. And what we saw in a previous lecture, I'm not going to reprove it today. If you want, it's in the lecture notes. You can see it there. Saw in a previous lecture, in particular when doing JL in class, when we first talked about JL, we can, like any choice of the yj's induces, I'll call it a Voronoi partition, P, which I'll call P1 up to Pk, on the set of points. So what is a Voronoi partition? That's just a fancy way of saying we're going to partition the points based on which center they're closest to. So P1 is the set of all the i's such that xi is closest to y1. P2 is the set of all points that are closest to y2. P3 is the set of all points that are closest to y3, etc. And then we can rewrite K-means clustering as, let's try to find the best partition, which minimizes the cost. So what we're going to say is we're going to find the best partition. Then for each partition separately, we can pick the best center for that partition, and then that's our cost. Now what you can show is once you fix the partition, if you ask now what's the best center for a particular partition, for a particular pj, what should I choose yj to be if I insist that pj is this set of points? Then you can show that the yj, which minimizes the sum of square distances within the partition, is the centroid. You can show that by taking a gradient and setting it to 0. The centroid is just the average point in the partition. You can show that the best choice of yj is, I'll call it mu j, which is the centroid. That's 1 over the size of pj times the sum over I in pj of xi. It's just the average. It's just the average of the points there. It's the mean. Okay. So we want basically the argument over partitions of the sum j equals 1 to k, 1 of the sum I in pj of xi minus mu j L2 norm squared. Okay. So I'm not going to go through the calculation laboriously today because this is something we've seen before, but K-means clustering can be rewritten in this way. Okay. Why is that relevant to constrained low rank approximation? So let me rewrite that. I said that we want to minimize the sum, j goes from 1 to k, of the sum I in pj of xi minus mu j L2 norm squared over all k partitions p1 up to pk of 1 to n. Okay. So why is this related to constrained low rank approximation? So we'll define a matrix. I'll call it A. What is this matrix? It has the xi's as its rows. The ith row is xi. Okay. So we're trying to cluster the rows of A. Okay. And I claim that any k partition, if you look at a k partition and ask what its cost is, I claim that can be expressed as the cost of projecting by a certain rank k orthogonal projection. Why is that? Let me give you an example. Let's say that these are the points we want to cluster. So the claim is that the cost of any K clustering can be expressed as I minus P A for Venus norm squared for a certain rank K orthogonal projection P. So, okay, so why is that? Let me just give you an example. So let's say we have 4 points and we're trying to cluster into 3 clusters. So here I have this, you have these 4 points. And then I have another point somewhere here. And then I have another point. And let's say that these points, let's label them. This is x1, x4, x2, and x3. Okay. Now, this is a particular 3 partition of the set of points 1 up to 4, right? And I'm just saying that if you have the same color, you're in the same partition. I could have partitioned these in other ways, but I chose this particular 3 partition of the 4 points. X1 and X4 are in the same partition. X2 is in its own partition by itself. X3 is in its own partition by itself. So I'll call this 3 partition P. I can now define a matrix. And that matrix is defined as follows. Okay. It's going to be n by k. So n here is 4 and k is 3. And it's some normalized point cluster indicator matrix. So xij is going to be 0 if point I is not in cluster J. Otherwise, I'm going to pick it to be a certain non-zero, and I'm going to pick it so that, you know, I'm going to get a projection at the end, an orthogonal projection at the end. So what am I going to do specifically? So let's say that the clusters are, let's label them. Red is cluster 1, black is cluster 2, and yellow is cluster 3. Okay, so x1 is in cluster 1. So I'm going to put a non-zero here. X2 is not in cluster, and it's not in clusters 2 or 3, so I'll put zeros here. X2 is in cluster 2, so I'll put a non-zero here, and then it's not in the other clusters. X3 is in cluster 3, so I'll put a non-zero here, it's not in the other clusters. And X4 is in cluster 1. Okay. Now, how do I fill in the non-zeros? I'll just fill them in so that the columns are orthonormal. Okay. Basically, what I'll just do is I'll make each, like if I pick a particular cluster, a particular column, I'll set each non-zero entry there to be 1 divided by the square root of the partition size. So in other words, these 2 things here, there are 2 of them. So I'll make each one of them be 1 over square root 2, 1 over square root 2. And then in this column, there's only 1 thing. I'll just put a 1 there. In this column, there's only 1 thing. I'll put a 1 there. Okay. So notice now XP has orthonormal columns. So XP has orthonormal columns, which implies that XP transpose is a rank K orthogonal projection. You might ask the question, Jelani, what if you choose to make one of the clusters empty? That's fine. If you make a cluster empty, just pretend it doesn't exist. So then now you only have K minus 1 clusters or something less than K clusters. So now XP will have fewer columns. It'll be a projection onto an even lower dimensional space. It'll be a rank K minus 1 or some rank K prime orthogonal projection where K prime is less than K prime is less than K. And in fact, I should say a PCP sketch, let me see how I defined it. What we're going to show today is everything is going to work even if it's rank at most K. So let's see here. Instead of all rank, at most k orthogonal projections. So it's going to preserve not only k clusterings, but if you choose to use less than k clusters, it'll preserve that too. That's fine. Okay. So now what we're saying is, okay, so good. So good. So I defined this matrix, but so what? So so observation is that if you look at XP transpose and apply it to A, the rows of this matrix are the centroids of the corresponding partitions. This is just a computation, which maybe I'll let you do offline. What I mean is, if you look at A, A is some matrix that looks like X1, X2, all the points that you're trying to cluster. And then you look at this matrix, XP transpose A. What I claim is that the centroid of X1's partition, the centroid of X2's partition, etc. I claim that it just maps each row to the centroid of the partition that row is in according to the K partition P. Okay, so that's just a fact based on how we defined XP. That's pretty easy to verify, which I'm not going to spend time on doing right now. Okay, which means this implies that the cost of that partition is exactly A minus XP transpose A for Beanies norm squared. Just look at it row by row. Row by row, this difference matrix is, X1 minus its centroid. Now for Beanies norm squared, we'll square that row's norm, plus X2 minus its centroid, square that, add it in, etc. Okay. So this implies that k-means objective is, like the min over all, I'll call it over all projection matrices P. I don't want to reuse P. P there was a partition. Let me use something else. Q in QK. QK is like the set of all rank K projections that look like, XP transpose for some K partition P. So it can be written as basically identity minus Q A Beanies norm squared. Okay. Which means if you have a PCP sketch, you can do sketch and solve. Okay. So good. Now that I've done a little bit of motivation, what I want to do is kind of write down the theorem. The theorem is going to say that as long as pi satisfies a certain number of deterministic, I think as long as pi satisfies 4 deterministic properties, those properties guarantee that it will be a PCP sketch for A. And what we're going to see is, one of the properties is going to be that it's a subspace embedding for a certain k-dimensional subspace. Okay. And the other properties are all going to be basically approximate matrix multiplication events, which, by the way, if you remember, one way to get AMM, approximate matrix multiplication with Frobenius norm error, is to have the JL moment property. So that was something we saw when we talked, the first thing we talked about when we talked about sketching for numerical linear algebra was, using it for approximate matrix multiplication. We said that one thing you can do is you can sample rows where the probability that you sample a row is proportional to its L2 norm. Okay, if you remember that. And then we said the other thing you can do is instead of sampling, you can do a kind of JL kind of sketch where you just pick an oblivious random matrix. And we said that as long as that distribution you're drawing from satisfies the so-called, epsilon delta JL moment property, which, JL matrices, which Gaussian matrices do, fast JL does, sparse JL does, count sketch does. If you're drawing from a distribution that satisfies this JL moment property, then with good probability, you will get approximate matrix multiplication for any fixed two matrices. Okay, so in other words, what we're going to see now in this analysis is if you have a subspace embedding, an oblivious subspace embedding. Okay, so let me put it like this: if your distribution over matrices pi satisfies two things at the same time, one, it's an oblivious subspace embedding. Two, it has the JL moment property. If it satisfies those two things simultaneously, then by a union bound over the events that we're going to need to condition on, you will be a PCP sketch with good probability for any fixed matrix A. Okay. And as you're going to see, based on kind of what errors we need, what dimension we'll need to be a subspace embedding for, it's going to turn out that, a random Gaussian matrix, for example, will be a PCP sketch as long as the number of rows is at least k over epsilon squared. Okay. We're also going to see that if you take, for example, a count sketch, count sketches also give OSEs. That was by Clarkson and Woodruff, and they also have the JL moment property. So if you use the count sketch, we're going to see that you're also going to get the PCP sketch as long as the number of rows is something like k squared over epsilon squared. Okay.
Can I ask a question?
Yeah.
So the sketch and solve bound implies that we can actually solve these optimization problems, right? But as far as I know, k-means it's like clustering. It's actually like you can't actually solve it, right? So
yeah,
how do you get bounds on like actual algorithms? Is there a way to?
That's a very good question, and we're actually going to talk a little bit about that, right after we finish talking about PCP sketches. But in fact, it's what you can show is you can even, like, if you just approximately solve. If you approximately solve the sketched version, you don't have to optimally solve it. Okay. If you approximately solve the sketched version, that also will imply that the solution you find is approximately solving the original version. Maybe we can even see that right here. So if you look here, right, kind of, I think the thing that will change in the analysis basically is just this inequality right here. Right? So what you're saying is, look, when I have the sketched version for k-means, let's say, or even for some other constrained low rank approximation problem, it might be very hard for me to find p tilde star. P tilde star is the optimal projection for the sketched version. And k-means is an NP-hard problem, right? But maybe I have some approximation algorithm that lets me find some other p tilde, where p tilde is it's not the optimal, but let's say it's guaranteed to be at most alpha times the optimal. It's an alpha approximation algorithm. Now what I can say is, basically here, I can say identity minus p tilde times blah, blah, blah squared is at most alpha times identity minus p tilde star times blah, blah squared. And then now I can replace that p tilde star with p star, just like I did here, and then continue. So what you'll end up getting is that, if you can alpha approximate the sketched version, the solution you find there will be within alpha times 1 plus epsilon of optimum for the original non-sketched version. Does that make sense?
Yeah, I see. Thank you.
Yeah, no problem. So yeah, even it doesn't have to be, it's not just that optimality carries over to approximate optimality. It's also true that approximate optimality also is lifted to approximate optimality. You don't have to optimally solve the sketch version. That's a very good question. Any other questions? Okay, so if there are no other questions, let's prove the theorem. State the theorem and prove it. So actually, before I state the theorem, let me state one other auxiliary lemma that I don't actually need to state and prove the theorem, but when I state the theorem, I think it'll help you to know that this lemma is true. Okay, so recall. I meant to use black ink. So recap. we say pi is drawn from a distribution with the epsilon delta pjl moment property if for all vectors u of unit norm, we have that if you look at the LP of pi u L2 norm squared minus 1 LP norm. So here again, remember, this means expectation of that thing to the p to the 1 over p. If this thing is at most epsilon times delta to the 1 over p, yes, that's it. Okay, so that's the definition of what it means to satisfy the epsilon delta p JL moment property. Okay, and we've already talked about this before, and we said if you have this for p at least 2, then pi will also give you the approximate matrix multiplication as well. Now I want to show you that the JLMP gives you something else as well. Suppose pi drawn from a distribution with the epsilon delta p JL moment property for some p, which is at least 1. Okay. Then for any matrix M, I have that the probability over pi of pi m Frobenius norm squared minus m Frobenius norm squared is bigger than epsilon times what it should be, is at most delta. Okay. So does this make sense? This looks a lot like distributional JL, right? Distributional JL says for any fixed vector, you preserve its L2 norm with high probability. This is saying that if your distribution pi for pi also if it gives you distributional JL for vectors and it gives it to you via the JL moment property, then not only does pi preserve the norm of vectors, it also preserves the norm of matrices for free under Frobenius norm. Okay, and this is not a complicated lemma. We can prove it right now. It's basically via the triangle inequality using the fact that this norm on random variables is in fact the norm, right? This thing is in fact the norm on random variables, and we're going to use that fact. So say M looks like this. It has columns M1, MD, let's say. Okay. Then we know that, if you look at M Frobenius norm squared, you can just do it column by column. And if you look at pi M Frobenius norm squared, you can also do that column by column. So that implies that if you look at the p norm of pi m Frobenius norm squared minus m Frobenius norm squared, just by triangle inequality, this is at most the sum over all I of the p norms of these things. This is now L2 norm squared minus mi L2 norm squared. And then you can just divide mi by its norm and then carry the norm out to the outside and then just apply the JL moment property. So what the JL moment property says is that this is at most the sum over I of the norm squared of mi times epsilon delta to the 1 over p. But of course, this thing here is just the Frobenius norm squared of m. So this is equal to epsilon delta to the 1 over p times m Frobenius norm squared. Okay. And then now what do? You do Markov's inequality. This implies that the probability, let's just call this thing, let's just call this event like star. The probability of star occurring, okay, by Markov on the p, after you apply the pth power to both sides, is at most the p norm, exactly what's above here, the p norm to the p over epsilon to the p times Frobenius norm squared to the p. Okay, and that thing is at most delta. Actually, this is delta. So if you have the JL moment property, then not only do you preserve the norms of vectors, but you also preserve the norms of matrices under Frobenius norm for free. It's just a consequence of triangle inequality. It's nothing too complicated. So now that you've seen this, now I want to state the theorem for PCP sketches. And you'll see from the conditions, you'll be like, oh, that follows from GL moment property. That follows from GL moment property. That's a subspace embedding. That's GL moment property. So you'll just be able to, now that you're experts in all this stuff, you'll be able to basically read off kind of what sketch dimension you need to make this all work. So theorem, and this is due to the paper I said, Cohen et al. 2015. Suppose A is given and it's U sigma V transpose. That's the SVD. Okay. And also, we know that, so like AK denotes UK sigma K VK transpose, and A minus K denotes basically A minus AK. So in other words, it's, AK is like you project using UK transpose. A minus K is the orthogonal, you project to the orthogonal space. So you project using identity minus UK transpose, for example. Then if pi satisfies the following properties, four properties, okay, it is 4 epsilon comma K PCP sketch for A. So what are the properties that I wanted to satisfy? First, pi is an epsilon subspace embedding for the row space of AK. AK is a rank K matrix, so its row space has dimension K. So this means you have to be an epsilon subspace embedding for a particular subspace of dimension K. So again, if it's a Gaussian matrix, if pi is Gaussian, then how many rows do you need? K over epsilon squared. If it's a count sketch matrix, you need K squared over epsilon squared, etc. I actually added a table to the course notes. So if you look at the course notes, let me actually pull up the course notes myself. If you look at figure 6.1 in the course notes, it's in one of the subspace embedding sections. It just lists for a bunch of different distributions, like how many rows do you need to make that distribution be an OSE, an oblivious subspace embedding. So, if you ever just need a table to look at, it has it for kind of sparse subspace embeddings for count sketch, for the fast JL transform. Also, it has it for non-oblivious ones, such as, for example, leverage score sampling. But if you don't have that thing memorized right now, that's okay. But basically, this requires K over epsilon squared rows. You can get away with K over epsilon squared rows. Okay. What's the second thing you need? The second thing you need is, if you look at A minus K pi transpose Frobenius norm squared minus A minus K Frobenius norm squared. Okay. I want this thing to be at most so let me not square it. Yeah, this is Frobenius. Yeah, Frobenius norm. Oh, I know what happened. This thing is not should be there. Okay. I want this thing to be at most epsilon times A minus K Frobenius norm squared. So let me just write in red. So this is subspace embedding. This is epsilon subspace embedding for dimension K. This is approximate. This is actually the lemma. Let me number that lemma. So let's call this lemma 1 for today. Right. Lemma 1 says if you satisfy the JL moment property, then it implies that not only do you preserve vectors, but you also preserve matrices. Okay. So this is basically It was basically the JL moment property. So this is like the epsilon delta p JL moment property by lemma 1. Okay. The other thing you want is you want approximate matrix multiplication. So in particular, if you look at A minus K transpose minus the sketched version, which is A minus K pi transpose pi A minus K transpose Venus norm. That's exactly approximate matrix multiplication. You approximately multiplied two matrices by first sketching them using pi, and then asking now what is your error, and I want my error to be at most epsilon over root k times A minus K for Venus norm squared. So if you remember, the connection between JL moment properties and approximate matrix multiplication, this basically means you need epsilon over root k, comma, delta p JL moment property, by previous lectures. And then the fourth one is also going to be an approximate matrix multiplication. So now what I'm going to do is I'm going to look at, pi vk transpose pi A minus K transpose. Okay. And I'm going to look at the Frobenius norm squared of that. And I want that this thing is at most epsilon over root K times the Frobenius norm of Vk times the Frobenius norm of A minus K. Again, this is just straight up approximate matrix multiplication. Why? Because remember now, Vk and V minus K are orthogonal to each other, right? V minus K is like the orthogonal subspace to Vk. So if you look at, if you were to look at what's the actual, pretend it was not sketched, and ask yourself just like, what's the actual matrix product? Well, it's Vk transpose times A minus K transpose. Okay. But A minus K, A minus K, okay, so A is U sigma V transpose, which means A transpose is V sigma U transpose. So this thing here is just V minus K sigma minus K U minus K transpose. But now Vk transpose V minus K is equal to 0, right? Because the columns of Vk are orthogonal to the columns of V minus K, right? The columns of Vk are the first K columns of V. The columns of V minus K are the other columns of V. All the columns except for the first K columns. And remember now, V has orthonormal columns. So the first K columns are orthogonal to the remaining columns. So all those dot products there are 0. So, you could imagine that you actually had a minus Vk transpose A minus K transpose here. Then it looks exactly like AMM. But the point is you don't need that because this is just 0. Okay. So how do you get this? Again, you get this via the JL moment property, epsilon over root K delta P JL moment property. Again, by the previous lecture when we talked about approximate matrix multiplication. Okay, so I know that maybe it looks scary. It looks like a mouthful. There's a lot of stuff, a lot of symbols, but basically, again, as I said before, it just boils down to two things. What are the dominant things here? The dominant things are, one, you need to be an epsilon subspace embedding for dimension K. Okay, you need to be epsilon JL moment property, but you also need epsilon over root K JL moment property, which is even harder because that's even smaller error. So then you also need this. Okay. So as long as your distribution for pi has both of these properties, you will be, with good probability, a PCP sketch. Just by union bounding, imagine you set delta to be delta over 4. Then you union bound over all these 4 events, that you satisfy all these 4 events simultaneously, and you're golden. Okay? So any questions before I dig into showing why the theorem is true? Why is it that if you satisfy these 4 conditions, you're a PCP sketch? Questions about the statement or about anything that I'm saying? Okay. If not, then let's begin the proof. So proof, and I know like I don't expect you to keep these 4 conditions in your head. So I may occasionally have to flip back to this page just to be like, oh, look, that's condition 1, that's condition 2, etc. Or maybe I'll just state it and have you trust me that that was one of the conditions that I wrote down. Okay. So our goal is to show what? That for all P and OK, OK again is, remember, it's the set of all rank K orthogonal projections that we have 1 minus epsilon identity minus P A for being norm squared is at most, when you have the pi, the sketched version, etc. Now, I'm just going to from now on just write identity minus P as Y, because otherwise I'll go crazy writing lots of letters. And, fact, the Frobenius norm squared of a matrix is just equal to the trace of M transpose M. Okay. It's also equal to the trace of MM transpose. Okay. I guess this here is like the so-called cyclical property of trace. Namely that trace of AB is equal to trace of BA. Okay. As long as the dimensions make sense. So as long as, A times B might make sense in terms of matrix dimensions, whereas B times A doesn't. But the claim, this is just a fact you can easily verify by the definition of trace and the definition of Frobenius norm. Or here the definition of trace. As long as A and B have conforming dimensions, and as long as, I guess this means that A and B have to be square. But basically, as long as this makes sense in terms of dimensions, then it's true that the trace of AB and the trace of BA are the same thing. Okay, so that means that you can move this M over here, right? And you get trace of M transpose. Okay, good. So now I'll define C to be AA transpose. That implies that if you look at kind of YA Frobenius norm squared, that's just equal to the trace of YA A transpose Y transpose. But Y is a symmetric matrix, right? Y is a projection matrix itself, right? It's the projection onto the orthogonal space. So any projection matrix can be written as QQ transpose for some matrix Q with orthonormal columns. So QQ transpose, the transpose of that is QQ transpose. So any projection matrix is symmetric. So Y transpose and Y are the same thing. So I can get rid of this transpose. And this is just C. So what I want is that for all Y that come from OK, for all Y, what I have is that 1 minus epsilon, the trace of YCY. Okay. Is at most the trace of Y A pi transpose pi A transpose is at most 1 plus epsilon times the trace of YCY. Good. This is the equivalent. This is what I want to show. What I'm going to do is I'm going to decompose A as AK plus A minus K. Okay.
Should there be an extra y at the end of the second, or at the end of the second trace you wrote?
Yes. Right there. Yep. Thank you. Is that the one you're talking about?
Yeah.
Okay, good. Yes, I put it there. Thank you. So I'm going to decompose A as AK plus A minus K. And that implies that if you look at the trace of Y, A pi transpose pi A transpose Y. Okay, I know that again, that's a mouthful. So now I'm going to substitute in A as AK plus A minus K. And I'm going to substitute it again in, this is the same as AK transpose plus A minus K transpose. And then I do some distribution. I'm going to get 4 terms, right? And it's going to look something like the trace of Y AK pi transpose pi AK transpose Y plus the trace of A minus K pi transpose pi A minus K transpose Y. And then I get the cross terms plus the trace of Y AK pi transpose pi A minus K transpose Y plus the trace of A minus blah, there's a Y there. A minus K pi transpose pi AKY. AK transpose Y. Okay, sorry, again, it looks like a mouthful, but hopefully what I'm doing is not, even though it looks like a lot of symbols, I think I'm not doing anything conceptually complicated right now, right? I'm just I'm decomposing A as the projection of the columns into one subspace plus the projection of the columns into the orthogonal space. So that's AK plus A minus K. So now, remember now, I want to understand these 4 terms minus the trace of YCY. And I would like to say that when you look at the difference, it's at most epsilon times the trace of YCY. So I can do the same kind of decomposition for YCY and also get 4 terms. And then now let's look at those 4 differences separately. I'm going to define them now. I'm going to define E1 to be the first difference, which is now AK transpose, okay, minus AK pi transpose pi AK. I'm going to define E2 to be the version with the minus Ks, A minus K transpose minus A minus K pi transpose pi A minus K. And then, you probably guessed it, I have to deal with the cross terms as well. Okay, so this is A minus K pi transpose pi AK. Okay, why didn't I write down, the version without the pi's? There should be a transpose here. I forgot some of my transposes. Why didn't I should also write down, minus A minus K AK transpose. Why didn't I do that? Right. I could have also said, there's a minus here, A minus K. I want to look at the difference between the non-sketched version, AK transpose. Like, why didn't I write that down? Any takers?
It's 0.
Yes, it's 0, right? Again, because what is this? This is U minus K sigma minus K V minus K transpose. And the other thing is VK sigma K UK transpose. And this right here is 0. Again, because those columns of V are orthogonal to the other columns of V. So I don't have to write this. It's 0. And then E4, we'll look at the similar other part, AK pi transpose pi, A minus K transpose, right? And why am I doing this? Again, if you look at the previous whiteboard, I'm trying to compare this with the version that doesn't have the pi's, which is this. So right, what I want that the trace of y a pi transpose pi a transpose y minus the trace of y cy, I want this thing to be at most epsilon times the trace of y cy. Okay. But this now is exactly equal to the trace of ye1y plus the trace of plus ye2y plus ye3y plus ye4y. And trace is a linear operation. So this is the sum, I goes from 1 to 4, of the trace of y eiy. Okay. So if I can show that each one of these things is small, if I show that this thing is at most epsilon times the trace of ycy, then I'm done. I'm golden, right? Because I'm getting 4 of them. I get 4 epsilon trace of ycy as my error, which is exactly the theorem statement. The theorem statement said I'm going to be a 4 epsilon PCP sketch. That 4 is exactly because there are these 4 terms that I'm going to bound separately. Each one is going to give me epsilon. Okay? So that's where we are. Now it's just a matter of executing, namely showing that each one of these 4 terms is bounded the way I want it to be bounded. So before we execute, any questions about where we are or how we got here? Sorry, and I see that there's a question in the chat. Let me pull it up.
We were just talking about the trace.
Oh, yeah. Yeah. Okay. So any questions about where we are, or shall I continue? Okay. So good. Let's just do them one at a time. Okay. So let's now focus on E1. So the trace, so let's just say that, Y is a matrix. Let's write it down. It has certain columns. Let's just call these columns Y1 up to, etc. The trace of YE1Y, what is that? That's just equal to the sum the sum over I of AK transpose YI L2 norm squared minus the sketched version. Okay. And then now, what do I know? I know that pi is an epsilon subspace embedding for the row space of AK, right? AK transpose YI is a vector in the row space of AK, right? So this thing is at most the sum over I of epsilon times the norm squared of AK transpose YI, which is exactly equal to epsilon times the trace of y, I'll call it CK y, where CK now is, remember, C is equal to AA transpose. So CK, what I mean there is basically AK transpose. Okay. And this thing is at most epsilon times the trace of YCY. Okay. So E1 was very easy. Okay. Questions about this before I move on to E2? The other ones are the ones that are going to be a little more complicated. So if you have questions about this one already, then you should speak up. Okay. So let's now do the other ones, which, there are a couple of clever tricks here and there. So, okay, what is E2? First of all, E2 is the version with a minus K, right? This is E2. So it's the version with minus K. Okay. So remember now, what is Y? Y is just equal to identity minus P, right? Where P is a rank K orthogonal projection. So we're looking at the trace of Y E2Y. Okay. This is equal to, this is the cyclical property of trace now. This is equal to trace of YY E2. Okay. Y squared. What's Y squared? Any takers on that? Anyone feel comfortable with their linear algebra?
It's just Y again.
Yeah, Y is a projection matrix, right? It's an orthogonal projection. So, right, projections are, what's the linear algebra term? Idempotent, I think, right? If you take a projection squared, you get back the same projection. I mean, that makes sense, right? A projection matrix looks like UU transpose. If you square UU transpose, you get UU transpose UU transpose. In the middle, you have a U transpose U, which is just identity. So you have UU transpose again. Okay. So any projection matrix squared, you just get it back. So this is the same thing as the trace of YE2, which you remember what Y is. This is equal to the trace of E2 minus PE2. Okay, and now let me use triangle inequality. This is at most the trace of E2 plus the trace of PE2. Okay. Now what's the trace of E2? What is E2? It's the version with the minus K. So let's just write it. What is this thing? This is equal to the trace of A minus K transpose minus the version with pi's. A minus K pi transpose, pi A minus K transpose. Okay. And again, just remember the other fact that trace of MM transpose is the Frobenius norm squared of M. And also trace is linear. Trace of A plus B is equal to the trace of A plus the trace of B. So I can apply linearity to separate out that minus sign, and then I get a trace minus another trace. Each one of those is of the form MM transpose. So this is the difference of two squared Frobenius norms. This is just A minus K Frobenius norm squared minus A minus K pi transpose Frobenius norm squared. Right? And this was one of the conditions. So if I go back to my conditions, yeah, right. This the second condition. It says that when you apply pi on the right, it preserves the Frobenius norm. So that was one of my conditions. I'm not making stuff up here. Okay, so let's use that condition. So this is at most now epsilon times the norm of A minus K Frobenius norm squared. Okay. Now, what do I know about A minus K Frobenius norm squared again? So now let's just remember we're trying to get bounds that look like trace of YCY, right? Remember now, we want errors that are at most something like epsilon times the trace of YCY, which if you remember, what does that mean? That just means epsilon times the Frobenius norm squared of identity minus PA, this thing, right? Trace of YCY is exactly that, where P is some rank K orthogonal projection. Okay. What is A minus K? A minus K, did I forget a Y? Oh, that's just answering a previous question. So what is A minus K? A minus K is the error you get left when you apply the optimal rank K approximation to A. So A minus k is like I minus p star times a, where p star is the best rank k orthogonal projection. Okay, so in particular, the norm of a minus k is only smaller than or equal to the norm you get by applying I minus p. So this is at most epsilon times I minus pa for the term squared, which is just epsilon times the trace of ycy. So I'm happy with that. Okay. So I'm happy with this part. Okay. Now what do I do about the other part? Okay. For the other part, what I do is the following. Okay. Remember now, the trace of a matrix, PE2 is a real symmetric matrix. Right? What is its trace? Its trace is the sum of the eigenvalues. Okay. So by Cauchy-Schwarz, the sum of the eigenvalues is at most the L2 of the eigenvalues times the rank of the matrix. Okay. What's the rank of PE2? So this is the sum of the eigenvalues, which is at most square root of the rank times the L2 of the eigenvalues. What's the rank of PE2? Well, it's at most the rank of P. And P has rank K. It's a rank K orthogonal projection. So the rank is at most K. So this is at most root K times the L2 norm of the eigenvalues. What's another way to write the L2 norm of the eigenvalues? Anyone? Yes, Frobenius norm. So this is just the Frobenius norm of E2. So I guess what I'm using is it's really PE2. But again, P is an orthogonal projection, so P cannot increase the norm of anything. So this is at most the norm of E2. And this is the thing that we just bounded, which is at most so this thing is at most basically, was this one of my conditions? Yeah. So this is condition 3, right? This is just E2. Okay. So condition 3 says that the Frobenius norm of E2 is at most epsilon over root K times a minus K Frobenius norm squared. So that's exactly what I have here multiplied by the root K. So the root K goes away. And this is at most epsilon times a minus K Frobenius norm squared. Right, which is exactly the same thing that I already had here. Right? It's the same thing. So this is at most another epsilon times the trace of ycy. Now that I look at this, I think I might need to slightly adjust my theorem. Not in any way that matters that much, but I think this 4 epsilon needs to be a 5, maybe. Let's see if I forgot another epsilon. Maybe I need to make it a 6. Right. So the point is, when I handled E1, I picked up 1 epsilon. When I handled E2, I actually picked up 2 epsilons. Right. This one and this one. And then, so that's 3 so far. I think E3 is going to give me another one, and then E4 is going to give me another one. So I think I'm going to get 5 epsilons altogether. Okay, so let's continue our march onward. So what is E3? E3 is, where is E3? Here. E3 is I have an A minus K and I have an AK. So it's one of the cross terms. Okay. First thing to note about E3 is that both E3 and transpose are in the column spaces of A. Okay. So how am I going to use that fact? So this thing here is, what is E3? It's equal to, was it minus K or K? Minus K. A minus K pi transpose pi AK transpose is in the column space of A. Also, E3 transpose is also in the column space of A. So this, in particular, this implies that if you look at CC pseudo inverse, right? Any matrix, if you take AA pseudo inverse, that's just we talked about this before when we defined pseudo inverse. AA pseudo inverse is the projection onto the column space of A. So CC pseudo inverse is the projection onto the column space of C, but C is just AA transpose. So the column space of C is the same thing as the column space of A. So this is just the column space of A. So CC plus is just the projection on the column space of A. So if you apply it to E3 transpose, this is just E3 transpose, right? Because E3 transpose has columns that are already in the column space of A. So if you project it, you're not changing anything. So now let's start doing some computations. So if you look at the trace of Y, E3Y, again, okay, so this is the same thing as the trace of the transpose, right? The trace of A and the trace of A transpose are the same thing. That's all I'm using here. And again, I can use the cyclic property of trace to move the Y over, use the fact that Y squared is equal to Y. So this is the same thing as the trace of Y E3 transpose. Okay. And then now I can use the property that I just said. If you project onto the column space of A, you get back the same matrix E3 transpose. So let me just put that projection operator in there. It doesn't change anything. Okay. And then now this is, let me write this down. You might not be familiar with this notation, but I'll explain what it means. Okay, so what does it mean to take the square root of a matrix? So whenever matrix functions, if you take let's say M is equal to like U sigma V transpose, where sigma is equal to like this matrix that has all the singular values in the diagonal. When I say f of sigma, what I mean is you'll apply the function to each of the sigma i's separately. This is just notation. And now f of m is just defined to be U f of sigma V transpose. So when I say C plus to the 1/2, what I mean is take C plus, write its SVD, and then just apply this square root function to each singular value separately. Okay. Now, what do I know about C? C is a real symmetric matrix, right? In fact, it's PSD, right? So I can, because it's real symmetric, by the spectral theorem, I can write C as, well, I mean, first of all, we already know what C is. I mean, notice that C is equal to AA transpose, which if you expand out what, A is U sigma V transpose. So this is just U sigma squared U transpose. In other words, C plus is equal to U sigma minus 2 U transpose. So when I say C plus to the 1/2, what I really mean is U sigma to the minus 1 U transpose. Right, so now you can just easily verify C plus 1/2 times C plus 1/2 is in fact C plus, which is U sigma minus 2 U transpose. Okay. And then now what I'm going to do is I'm going to use Cauchy-Schwarz. So you can define dot products on matrices, inner products on matrices, where you say like, I just define A dot B to be the trace of A transpose A, A transpose B. And, you know, if you just, so basically what does this mean? It means like treat A and B as, it basically means treat A and B as big vectors and take their dot product as vectors. So let's say A is an n by n matrix. Treat it as an n square dimensional vector, treat B as an n square dimensional vector, and take their dot product. Okay. So we know by Cauchy-Schwarz that when you take the dot product of vectors, it's at most the norm of the first vector times the norm of the second vector, the L2 norm. So here we want to take the L2 norm of A times the L2 norm of B. If you treat A as a big vector, what's its L2 norm? That's the Frobenius norm. So this means that Cauchy-Schwarz for this inner product is at most the Frobenius norm of A times the Frobenius norm of B, which if you remember what Frobenius norm means, this is just the square root of the transpose of A transpose A times the square root of the transpose of B transpose B, right? That's just what Frobenius norm is. So if you apply that Cauchy-Schwarz here, you get that this is at most square root of the trace of y c plus cy, okay, times the square root of the trace of E3 C plus E3 transpose. I know this is a lot of symbols to maybe you're getting lost in all the symbols, but all I'm using is I'm using this. That's all I'm doing. Okay. Now, I can simplify this further. What's another name for CC plus C? If you haven't, if you're not used to seeing this, again, just remember CC plus is the orthogonal projection onto the column space of C. So what is CC plus C?
C.
Yeah, you project C onto its own column space, so you get back C. So this is equal to the square root of the trace of YCY times the square root of the trace of the other thing. Okay. Okay, so now, so let's go to the next. This is the part that maybe will, so we know so far we're up to this. Trace of YCY times the square root of the trace of E3 C plus E3 transpose. Okay, so now what is E3? E3 is this thing over here. So we said E3 now, just remember what E3 is. It is equal to A minus K pi transpose pi AK plus, AK transpose, sorry. So if you write down in terms of the SVD, this implies that E3 is equal to U sigma V minus K transpose pi VK sigma U transpose. Okay. And also remember that C plus is equal to, what did I say, U sigma minus 1 U transpose. So this is going to look like a mouthful, but I promise you, and I think I'm almost out of time, so let me not bother even trying to do this in front of you, because it's just a bunch of symbols. If you just now look, what do we have here? We have E3 C plus E3 transpose. I've told you what E3 is. If I expand it in terms of the SVD of A, E3 is this. And I told you that C plus is this. If you just plug these two things into here, okay, I promise you that what you're going to get is, so you still have that trace of YCY. What you're also going to have is something that looks like times the trace of A minus K pi transpose pi VK transpose, okay, times pi transpose pi A minus K transpose. I know that looks like a mouthful. And this now, and there's a square root. Okay. And this is equal to square root of that thing times this you can write as the trace of MM transpose for a particular, no, a trace of AB transpose for a particular A and B. Sorry, what I wanted to say is you can express this now as like the trace of MM transpose, which is just the Frobenius norm squared of M for a particular M. And what is that M? It turns out what you're going to get is, and there's a square root here. It turns out the Frobenius norm you get is pi VK transpose times pi A minus K transpose. And then this is the Frobenius norm of that. And lo and behold, this is again approximate matrix multiplication, right? VK transpose A minus K transpose is again 0 because the rows of VK are orthogonal to the rows of A minus K. So this is basically again approximate matrix multiplication between VK and A minus K transpose. And that was also our final condition here, or maybe it was our third condition, I don't remember. Yeah, it was our final condition, which was an approximate matrix multiplication condition, which was this. This thing is bounded. And again, this thing is at most the square root of the trace of YCY, right? Because again, by the same thing we said before, A minus K is the optimal thing. It's the optimal error after you project with a rank K orthogonal projection. So it does better than what P would do. And P gives you the square root of the trace of YCY. So all in all, you're going to be happy. Okay, is the summary. So all in all, this thing is going to be at most, again, some epsilon times the trace of YCY. And then E4, I'm out of time. E4 is just equal to E3 transpose. So it's the same argument, right? Because what we want is we want to, and that's exactly what we just bounded, right? We actually just bounded this. This is the same thing as the trace of Y, E4Y. So we've already actually bounded it. Okay. So that's it. I know that looked like a lot of symbols, but it will be uploaded to the course notes within today. So you can take a look at the calculations more slowly if you'd like. So let me pause. That's it. And any questions?
I have a question about E2. So projection